Welcome, Physics 106. I'm Gannon Jones, and I'm going to be talking about radiation, damage, and protection today. Now, radiation is very much a part of our everyday life. I've written some examples down of where we come across it, such as nuclear energy, which could be a very useful source of very efficient and clean energy that can power our cities potentially in the future. We have X-rays, which we know from our medical visits or from our dental exams, helps us look at our bone structure. Very useful considering we don't have to open ourselves up to see our bones from now on with the invention of the X-ray. We know our microwave oven, which comes from heating our foods every day. We are very blessed to have the microwave technology. And UV radiation. Now, most often we see UV radiation in our day-to-day life coming from the sun. And as helpful as these types of radiation are, it's very important and useful to realize that they can be potentially damaging, and we need to know how to seek protection from them. We all know from spending too long in the sun, the next day we can attest that for sure radiation is quite damaging. Now I have two types of radiation listed here and a couple of examples in each type. We have particle beams, which is radiation in form of a physical matter providing the energy. Okay. For example, when atoms are unstable, they will often undergo a type of particle beam radiation to fall into a more stable state, often changing the identity of the atom. Here I have the 222 isotope of rubidium. Rubidium in this state has too heavy of a nucleus, too many protons and too many neutrons. So in order to go to a more stable state, it will often emit what's called an alpha particle. Now, an alpha particle consists of two protons, as indicated by the bottom number, and two neutrons, which forms an atomic mass of 4, indicated by the top number. Releasing two protons and two neutrons helps rubidium form a more stable element, in this case, radium, the 218 isotope of radium. Alpha decay is useful for unstable atoms which have too heavy of a nucleus. If radium-218 tends to be too unstable because of its nucleus, it can continue emitting alpha particles, decreasing its nuclear mass until it's energy stable. Sometimes a nucleus has too many neutrons, such as the isotope 227 actinium. And in order to replace a neutron with a proton, actinium will emit a beta particle, which is a negatively charged particle of negligible mass. This beta particle is emitted from a neutron, forming that neutron into an additional proton within the nucleus. When we change the number of protons, we'll change the identity of the atom into the isotope 227 thorium. With its neutron to proton ratio more balanced, thorium is more stable. Beta decay happens to unstable atoms because they have too many neutrons. If it's still unstable, still has too many neutrons, it can continue emitting beta particles. The other type of radiation comes in electromagnetic waves. The potentially damaging electromagnetic waves are gamma rays, X-rays, as previously mentioned, and UV rays. Electromagnetic rays has no mass, yet can still be ionizing to organic molecules and tissues and thus damaging. If we were to compare the damaging effects of these different types of radiation, we can get a grasp on the danger level we face when we confront each type. The main worry of radiation is its ability to reach our organic tissues and molecules, to ionize them and cause a lack of proper function. So we're going to look at the penetrating ability of these different radioactive sources. If we were to place paper, aluminum, and lead in front of radioactive sources of alpha, beta, particles, and gamma radiation, we can clearly see a difference of the penetrating ability. For example, if we were to shoot an alpha particle at these three objects, we would find the alpha particle gets embedded and stuck in a simple sheet of paper. This is because an alpha has a heavy mass compared to the other types of radiation, consisting of those 2 protons and 2 neutrons. So it's easy to block. And paper we can equivalent to our skin. Often our skin can very readily block alpha particles, and knowing that our skin is mostly made up of dead cells in our dermis, we can be quite safe when compared to other radiations. Now, beta particles has the mass equivalent to about 1 electron, which is very much lighter and massless in comparison to an alpha particle. It will blast right through paper, only stopping at the aluminum. This we can compare to our more superficial tissues. Beta particles can often penetrate our skin, and when it reaches live cells and molecules with a function and a purpose, it can often disrupt that, and we can see damage. But luckily, our tissues is not nearly as important of our vital organs, such as our lungs or our hearts. Beta particles cannot often reach that, but gamma can. Gamma radiation, as you know, has no mass, and thus is very difficult to stop, blasting through our paper and our aluminum. And usually it takes a good amount of lead before we stop a significant amount of our gamma radiation. Unfortunately, this could reach our organs if we were in front of a source of gamma radiation, and compared to our penetrating ability, we know that gamma radiation could be the most dangerous for us, and which is one of the reasons why we really need to have new technology to be able to protect ourselves if we were to continue researching these types of radiation. Now let's talk about specific damage that can happen. I have here 2 thymine nucleotides on a DNA backbone. Thymine is one of the nucleotides that make up our DNA. And when we have 2 thymines adjacent to each other on our DNA backbone, we have the potential for some unwanted chemical reactions. I've drawn the organic structure of thymine, and this will because radiation damage happens on a chemical level. We know that this bond that attaches our backbone to our thymine nucleotide has the ability to be rotated around. And if we have a thymine to rotate around next to an additional thymine, we get these two nucleotides with this two-line bond adjacent to each other. Now this second line means there's an extra pair of electrons that can react chemically if given enough energy. Now when we're out and about in the sunshine, UV light from the sun can provide that energy. When these two thymines are adjacent to each other with both extra sets of electrons around, this energy from UV light can push electrons to form new bonds, forming what we know as a thymine dimer. Now, our two thymines in our DNA are not supposed to be forming a dimer with each other and making one big nucleotide. This causes problems in our DNA, and during replication, it will stop the cell's ability to replicate, causing potentially cell death if it's not fixed. And even as the cell attempts to fix thymine dimers, there is potential for permanent damage done to the DNA. This is why we get sunburns. If we experience too many sunburns and our cells are constantly trying to fix thymine dimers, we could lead to skin cancer. And that is why it's important that science has discovered a useful ability to prevent sunburns in terms of sunscreen. So my example of protection from radiation also comes from UV radiation. And you'll notice that sunscreen can come in two different types, or you will be able to notice from now on. One type are chemical blockers, which uses chemical molecules such as avobenzene, which we place on top of our skin, and avobenzene is able to absorb UV light instead of our thymines. Very useful. Our second type are physical blockers, such as zinc oxide or titanium dioxide. And this really works like a mirror. They're little pieces of metal that just reflects UV light, so our skin doesn't even have to worry about it. So from now on, when you put on sunscreen, you know exactly the chemistry and the science that is going into protecting your skin. Other generic types of radiation protection comes in 3 steps. Limit your time. The less time you are bombarded by UV radiation, the less of a chance 2 of your thymines adjacent to each other can be hit with UV light at the right moment to form a dimer. Increasing distance helps. You see that there is much stronger concentration if this stick figure was closer to the source. He'd be taking twice as much energy as he is back here. And lastly, use shielding. If we just stay inside all day, then these UV radiation or whatever radiation is coming from this source is unable to reach us, and we'll be safe and sound. Thank you so much.